He loves music, open source software, and craft beer. So please tell him which beer is the most delicious in Japan. So the title is Compiling Ruby.
Yeah? How do I do that? Hi. Okay. Hi. Can everybody hear me? I'm going to start with a very quick story. Yesterday, I flew into Tokyo, and my flight to Hiroshima was canceled because of the typhoon. I do not speak Japanese. This is my first time in Japan. This is my first time in Asia. I know 4 words, and so I was in Tokyo, and I went up to people and I said, "Konnichiwa, Gaijin, Hiroshima, arigato." 10 hours later, I got here. I took 4 trains, but I'm here, and it's a great honor to be here. So thank you very much for having me. My name is Deisz. I work at a company called LoadIset in Boston. I don't think there's anyone else from Boston here, but if you are, please come find me and say hello. Hey, buddy.
I moved like a year ago.
Oh, okay. Well, anyway. Okay, so compiling Ruby. So this is our sample Ruby program, and it's very simple. And we go to our command line and we run it. We get 10, like we expect. So this talk is going to go through everything that happens in between the time where you write Ruby example.rb and the time you get 10. There are a couple things that were introduced to Ruby 2.3 that I'm going to talk about, and the things that you can do with that completely abuse that ability. So we're going to talk about the Ruby execution process. So code is first loaded with require, or load, or however it gets in there. Ruby goes and reads the source of the file. It goes and tokenizes each of the individual elements of that file. It goes and builds an abstract syntax tree from those tokens. Back in Ruby 1.8, we used to immediately interpret that AST, so we'll talk about that, but that's kind of old school. These days we build instruction sequences, and those instruction sequences then get interpreted by the virtual machine. So this is the Ruby execution process, and we're going to talk about this. So first step is tokenizing the input, and tokenizing is relatively well understood. You have your example here, and you go through and find each element. This is lexical analysis. It's not semantic analysis. We don't know at this point that this is Ruby. We just know that these are tokens. We don't have any actual information about the Ruby program, but we get the order in which this is done. And some different languages will do this in different ways. Ruby has rolled its own tokenizer. Oh, by the way, if I say anything that's out of date, it's because I didn't know it was out of date, but it might be, so just keep that in mind. Anyway, Ruby rolled its own tokenizer for this section, so this part is handled internally, but there are other tools out there. There's Flex and Braggle and other things, open source, that you can check out. And anyway, at some point we get our tokens. So we have our list of tokens, and then we can run through it. And we can go and build the abstract syntax tree from those tokens. So we walk down the list. And what it does is, this is called the recursive descent parser. Really popular one is Bison, and that's what Ruby is using internally. But you can use these, what you do is you match patterns. And you can go and define the grammar, and it'll do that for you. And so we go and we say, okay, this is a pattern. This is an assignment. This is a local variable assignment. So you end up with this tree. You end up with this tree structure where ident equals 5 new line. And then on the other side, you get puts a plus 5. And you end up with this tree. So at this point, we have a tree. And so we've gone from our source file to our tokens to our tree. We can take this tree and we can interpret it. And this is what used to happen immediately with Ruby 1.8. So we go through, and when you're interpreting an abstract syntax tree, you need two things. You need some kind of context object that moves along with the interpretation as it goes, and you need a stack. This is a stack-based virtual machine. So we can run through it from the beginning, and we'll go and we write Ruby example.rb in the command line, and we just start at the top. And we move down our tree slowly. I wish I had time to make better graphics for this, but basically it's a tree structure. You can imagine it's an actual tree. And we push 5 onto the stack, and then we push a local variable assignment. And what that's going to do is going to take that 5 and put it into the local table. And we can reference that later on in the execution process. We move on to the next pattern. We push a 5, we push a get local variable, which pulls out of that local table that we already assigned to. We get a 5 again. We send plus. This is a key point. When you're doing plus, you're sending a message to a receiver. You're not calling some kind of primitive operation. So any kind of send is going to pop the receiver off the stack and then pop the operands off the stack. So that ends up with 10. We push self onto the stack in order to get the receiver, and then we call puts, and we end up with 10. And that's interpreting the abstract syntax tree, and that can be done immediately, though in Ruby 1.9, we got YARV. And YARV introduced the concept of instruction sequences, and it turns out that this is actually a lot faster. So building YARV instruction sequences is the next step in all the modern Ruby implementations that are C Ruby. And so we can take that same abstract syntax tree and walk down it in a very similar way, except instead of interpreting things directly, we instead build this list of instruction sequences. So we walk through, and we get a put object. Put object is like push onto the stack. It's like what we were doing, except we're just building up this list. We get our variable assignment, and we slowly build up this list until we have everything. And so now that we have this list of instruction sequences, we can go and execute them. So we've run through it in the exact same way that we ran through interpreting the abstract syntax tree, except this time we're interpreting instruction sequences. And there was a lot of value to this. The virtual machine can do all kinds of fancy hacks to make it more efficient. Each of these instruction sequences actually points to the next instruction sequence, so it's a lot faster to execute. But it looks very similar from a drawing on a slide standpoint of you walk down the list, you slowly push things onto the stack and pop them off and execute as we go through. And that's it. So Ruby 2.3 introduced a new feature. It introduced the ability to take those instruction sequences that were previously compiled and write them out, and basically introduced a binary format that could be read and written that could be used to take that instruction sequences and put it into a file if you wanted to. So here's kind of the way that it works. Koichi introduced this about a year ago, a little more than a year ago. This is a little bit lower in that same part. I found this section. The rest of this talk is based on using this method. So don't tell Koichi. Anyway, so the way that this works is we go to our command line and we can write compile file. Compile file is going to return an instance of the RubyVM instruction sequence class that has all of the metadata contained in it for that program. You can then call toBinary on it, which returns a string. And that string is not human readable, but it contains a whole bunch of information, everything that's needed to execute that file. And then you can go and write that up to a file. And then if you ls, you see that that's there. You also see that it's really, really big. The example was 32 bytes. The example at YARV is 777. It has a lot of metadata, it has a lot of information. There's a lot of longs in there that keep track of everything. And then on the other side of that, we can read it back in into a string. We can load from binary, and then we can evaluate that, and we end up with 10. This in and of itself isn't all that valuable, you can't do this alone, or you can, it just isn't as helpful. The really helpful part is LoadIset. So LoadIset was introduced at the same time, and it allows us to modify this flowchart to add these two sequences. And what this does is, when we've built our instruction sequences, instead of immediately executing them, we can write them out to a file. And then the next time that that file would be required, instead of running through this whole process again, we just read those compiled instruction sequences and immediately execute them. And it turns out that it's about 30% faster on boot. It's not going to make your program actually run faster, but start up faster. It's actually pretty significant. So this is what happens internally. This is RB load internal 0. And this function is the one that's called when something is required. And it turns out that this little area here, which is if the instruction sequences can be found from RB isec load isec, then just continue on instead of doing the parsing. And RB isec load isec looks like this, and this is the key here. It's checking whether or not there's a function called LoadIset, which you have to define yourself. And if there is, it just calls it. Otherwise, it returns null. So this is the smallest example implementation that I could make up. But this actually works. So what it does is LoadIset is called anytime something is required. So everything's going to pass through this. And what's going to happen is the path to the source file is going to come in, and you're going to create another path for an isec file, and that can be somewhere in your system, or it could be part of another file. And you're going to say if it exists and it's up to date, if it's fresh, meaning that the source file wasn't modified more recently than the isec file, that you can just load those instruction sequences from the file instead of compiling. And otherwise, we go and we compile the whole file, and then we write it out to the file and return that. So we're monkey patching instruction sequence. This is the part where you go and create another file path, and this can be really anything, provided it's deterministic. This is checking whether or not the file is fresh. And finally, we go and we do the compilation if it's necessary. So there are two major examples out there. The first is Woodsnapping. It came out of Shopify. If you're not using it in your Rails apps, you should check it out. It's pretty great. It does a lot of stuff. It does stuff on optimizing your require paths, your load paths, to make sure that things are pre-scanned, which does a lot in and of itself. It also does this compilation, and this is the part of Woodsnap that does the compilation. This actually gets prepended into InstructionSequence, and this is the part that does the magic. The other example is Yomikomu. It's actually in the source of the Ruby directory, if you go and look at it. And it's got a whole bunch of interesting different storage options. You can check out the gzip files and things like that. So this is all well and good, and this is the Ruby execution process. So now we're going to show how to break it, and what you can do with this to have a little fun, and to maybe bring a little bit more value to it. So let's go back to our example implementation. And if we move this out into a separate sequence, instead of compile files, we're just going to compile the content. Then we can split this up. This is the fun part. We have a string containing Ruby source, and we have a method that we're going to call with that Ruby source. Now, we're not modifying the file. We're not modifying the source file, but we can modify this string as much as we want. And here's the thing. When LoadIset was introduced, the original point of it was to save on memory when Ruby was first booted up, and also to save on time. And it definitely accomplished that. But the other thing that it did was it opened up a window into the Ruby virtual machine. It opened up a window because now you can programmatically load your own bytecode, which means that we can do all kinds of fun things. So, for instance, we can start gsubbing the string. And for those of you that can't read that regex right off the top of your head, which should be most of you, This means that we can take this and go like that. Now, where's the value in that? Ruby is very flexible, as we all know, and one of the things about Ruby's flexibility is that you can override integer multiply. I don't know why you would ever do that, but you can. And that means that if we look at this, Ruby has to allocate 24, 60, and 60 onto the stack. It has to allocate 2 method calls. And this is not as efficient as some other languages, because some other languages will see this, and other languages are not as fun, and you cannot override multiply on the integer class. And they can go through a process of what's called instruction elimination, and they can take this out. And that just becomes the result of the expression. So what I want is I want to maintain this readability. I want to maintain the fact that I'm trying to think about the number of seconds in a day. And I want to be able to see 24 times 60 times 60, but I also want the virtual machine to take care of this for me. I don't want there to be 3 method calls inside of this method. So what this gsub does is, this is a compiler macro. We're treating the Ruby compilation process as if it has macros by putting in these gsubs. And this actually replaces 24 times 60 times 60 with the evaluated expression. It replaces it with the return value. And you can see that in the gsub. Whoa. Oh. I think we're good. I think we're good. Yeah, so let's do a little more. You can also do this. Date.parse is notoriously inefficient because it's incredibly flexible. Again, same trade-off. Date.parse actually can handle just about any single date format that you throw at it. But the much more efficient version is date.strptime because you're handing it the format that it needs to parse. So you can have this for a literal string. Date.parse, you have some string, and this is readable. You can see January 1st. I don't want to replace that with strptime. But now I can do this. And my little tilde d there, by the way, these tildes are all stolen from Elixir. Just straight up stolen. These are sigils. And this works, and this gets replaced by a more efficient date implementation. So does it work? It does. It turns out that it does. Built a gem. It's called Vernacular, and you can check it out. There's a part of it called regex modifier that I included here. I did. Oh yeah, here's the gem. And this is the part of the README that talks about the regex modifier, and you can see you can go and create your own. And what this does is it hooks into the compile chain, that LoadIset sequence, and you can build your own regex, and you can do all kinds of funny things. You can really break Ruby this way, so be very careful. And so what we've done is we've added to this flowchart, we've added this modify source step. But we can go further. This is that same fun part that we talked about earlier. And the thing about macros is that they work, but they don't work in this context unless you have more semantic information. And the way that you get semantic information is with an abstract syntax tree. So I need an AST at this point. So I found an AST. It's called the parser gem. Parser goes and parses Ruby source, not exactly the same way, but close enough for my purposes, and builds my own AST. Now, parser is not meant to be used this way. I'm completely abusing it. For instance, parser base.send, because what is method visibility, really? An instance variable set, but turns out that you can do this. Parser, as a gem, has built-in support for rewriting source. So what we can do is take this code and do this. For those of you that aren't Scala devs, this is saying that's the type of that method call. And I want this. I want this because this actually represents this. But I don't want to write that because that's annoying. I don't want to go and explicitly do this. I want my language to take care of this for me. And it turns out that you can write this and do weird stuff to the Ruby compile chain, and none of your code has to change. And you can just add this in. Another example is typed method returns. This is my version of a method return because I didn't want to mess with def. And this actually represents this. We wrap the body in a begin end. We say, is the return value the right type? And we return it and raise an error if it's not. So this is what we're actually representing. So this also works. This is part of the same gem. This is horrendous to build. You have to completely modify the way that parser handles the AST. And what this gem actually does is goes in, extends the .y file, calls rack live to recompile the file, and then loads it in dynamically. I would not recommend doing this in production. But it does work. And there is a rewriter that happens and everything is all good. So what we've done is added a whole other step, modifying the AST. But we can go a little bit further. We go back to the original file that was written out to binary, and we just hex dump it. You can see where I'm kind of going with this. We can look at this, and we can kind of find information in the Ruby source. I was thinking about this yesterday when I was in Tokyo. There was a very nice woman who understood that I didn't understand anything. And she drew me a very nice map in Japanese that I did not understand. And it said to get to Shinjuku, and then set to get from there to Tokyo Station to Hiroshima. And it was all in Japanese, and I handed it to people, and I said, please get me here. There's a little bit of analogy in there in the Ruby source. In compile.c, there's IBF header. Now, I do not understand what this is, but I do understand what this is. This is a map, and it tells you a couple things. Turns out that there are 3 major sections of this, and we can start to get information about it. So the first 4 characters are always YARV, which I just love, because that was really easy to replicate. Immediately after the header is always the platform that you're compiling for, and on my machine that's x86-64 Darwin. And it turns out from the header we can gather other semantic information. This is the whole header, this is the Ruby version, and we have 3 major sections of this dump. We have the list of instruction sequences, which are those instruction sequences that I previously showed, except with a lot more meta information, like a cache table, the local table, all kinds of line information. IDs are much easier to understand. IDs are symbols internally, and those are in there. And there's also the list of every object in memory. And so what you can do is fork Ruby, put in a whole bunch of debugging information into the to-binary method, and get a whole bunch of metadata out. And you can find where all these bytes are. And so moral of the story, LoadIset allows us to provide our own bytecode. So we can inject debugging code into Ruby to learn the binary structure of a YARV bytecode dump. So we can write our own code that compiles down to YARV bytecode. YARV bytecode is deterministic. It means that when it's in the file, it's going to be the same thing every time you load it in. And if it's the same thing in a file, that means I can write my own file and load it in as well. And it should work. So what we've done is we've taken this code, which was our example previously of LoadIset, and we've taken this content out, and we put a little if statement in here. And this was my version of naming things. But, so I wrote something called 2b. 2b is tiny Ruby. It does nothing. And it's not very useful, but what it is a proof of concept. And we've established a contract here. This contract is that it takes in a string and it returns an object that responds to 2 binary. In Ruby's case, it's returning an instance of the RubyVM InstructionSequence class. In my case, it's returning an instance of the 2B InstructionSequence class. And so what we've done is made this even more complicated by adding this. We require a file, we read the source, we send it off to a completely separate compiler that writes out instruction sequences, and that gets executed. Because we're writing YARV bytecode, we maintain interoperability with Ruby. This is really the key point. Ruby instruction sequences are a separate level from the Ruby source. They're divorced from that because 2 binary on Ruby instruction sequences creates a separate intermediate representation. So by having this, we can get the benefits of a compiler, like instruction elimination and macros, without having to write a native extension. You don't have to drop down into C. The other thing is it gets the benefit of all of YARV. You get garbage collection that you don't have to worry about. You get all kinds of good stuff. This is what a 2B file looks like. It only does mathematical functions because it turns out this is really hard. And this allowed me to not have rescues, not have instance variables, global variables, really anything. But what it does have, the one thing it does have, is instruction elimination. So in Ruby, this would be 2 method calls right at the beginning of that function. But we can eliminate that. We can go in, and before we compile down to YARV bytecode, we can write out just that evaluation. And then in Ruby, we can call that method. So does it work? Kind of. Not really. It works sometimes. I've been messing with this for about 3 months now. It works when, it used to work a lot, but what I was doing was writing out Ruby, compiling it, and then just straight modifying the binary. What I've been trying to do lately is write it out entirely, and it turns out that Ruby's not built for this. All of the methods that I need are static, and all the headers are internal. But it's getting there, and you can follow along on my GitHub. It's getting there, so I'm hopeful. The moral of the story, though, is that we've made this very, very complicated flowchart. But at the end of the day, this is what we care about. I want to just require a file, read the instruction sequences that are already written out, and execute them. And this is what happens with compiled language, and this is what you get the benefits of with Ruby 2.3 and all of the new additions. Oh. So what's next? I want to make 2B actually work. I go back and forth on the actual production use of it. You can use it, and it will give you small benefits, but at the end of the day, what it's doing is being a proof of concept for what it would be like if Ruby had a spec on its virtual machine. If you go and you see the JVM, and I hate to bring up the JVM, if you go and you see the JVM has a spec on how you can implement the instruction sequences that Java compiles down to. And every one of those instruction sequences is documented and listed, and you can go and build your own. And I want that for Ruby, because the Ruby virtual machine is awesome, and it's a big player, and it should be treated as such. And I think that pushing this boundary is going to be really good for Ruby in the long run. Thank you, that's all I have.
Thank you so much, Mr. Giri. So about 10 minutes is left. So Is there any question? Oh, sure.
So, what were the reasons you chose Ruby further, the Ruby further than instead of refer the Ruby official further for the HT modifier?
Yeah, I looked at Ripper. I also looked at the other one out of Seattle, RB. Can't remember his name, but
Therefore,
yeah, but the reason I chose Parser was because Parser had the rewriter support built in. And I wasn't sure if the other ones did or not, but it had the ability to rewrite the source in a very easy API. And so it was just the fastest that I could, not the fastest execution-wise, but the fastest for me to learn. So that's why I chose that one.
Thank you for playing the InstructionSequence. I wonder that there is a people using InstructionSequence internal, so I'm very happy to hear. So, 日本語で言うと、私が今の機能を作ったので、で嬉しいなっていう。I'm happy to hear you are using feature. So question. So it's just a comment. So you at last you said you want to make a specification for the YARV bytecode.
Mm-hmm. Yeah.
But so we don't use. So sorry. So for more correctly, I didn't do that because so the instruction sequence is internal data structure or something internal. So you say so if we fix the bytecode, then it is difficult to make new instructions or change the instructions or something like that. So for example, today's keynote, he introduced incompatibility of
the intern.
The instructions.
Yeah.
So I think that this is advantage. So we have advantage and disadvantage. So as you said, so make a specification. So it is easy to handling instruction sequence more and more, and you can make more tools. But something like that. So the same reason we don't expose node structure, AST structure in internal use in MRI.
Yeah.
So this is because of same reason. So we need to change the syntax.
Yeah.
So I'm not sure we can freeze the specification better if more and more, so 10 or 20 years, if we didn't change any bytecode, then it can be. But or make a specification for Ruby 2.5, so version specification we can do.
Right. Yeah. So in the IDF header, right after YARV, the first two fields are major and minor version, like 2.8. I mean, it's 2.3 right now, even though we're on 2.5. And I think that might be a solution to version it, to version the instruction sequence versions, and maybe have different interpreters. But then you have to deal with that. So I don't know. But we'll see either way.
So if you don't care the specific, so make a version specification, so we can document for the instruction definition files. So there is a special notation format, so comment as a comment. So if we write more and more description for each instruction, it will be a specification.
Right.
Is there any question?
Oh, just a quick one. Well, would it be possible actually to make use of these techniques to maybe to do more metaprogramming, right? So basically, you write a Ruby program to manipulate the ASCs and then get it to compile it. You know, it's just sort of like the way list macros work.
Yeah, you should check out that gem vernacular. It does it live on the fly, and yeah, I mean it's definitely where that could go. You don't have too much information when you're working on it because you have to have a lot of knowledge of the internals of the parser gem, unfortunately. But yeah, you can definitely write those kinds of crazy macros. It comes down to the flexibility of Ruby as well, though, because you may not know where a method is defined at compile time, because it could be changed. I mean, the example I always give is that at any point in a Ruby program's lifecycle, it could go and download another Ruby file from a separate server and then load it in and change everything. So I think that there's a limitation on that, but I definitely think it's possible to get some value out of the macros.
Are you using this in production?
Not at my job. I have a couple of side projects that I use it on. It's a good question. I wouldn't do AST modifications live. I would do those macros. But there's a trade-off too in if this were used on a real company's, a company's dime, and then you go and hire a new Ruby developer, and they see a date sigil in your code, they're going to ask you where you lost your mind and how long ago. So, take it with a grain of salt. I do think there's value in it. I do think there's a lot of value in seeing explicit dates like that, seeing explicit numbers, being able to bring information from your application into the way that you write code, information that's specific to your domain. But yeah, all of that with a grain of salt.
So, is there any question? It will be the last question.
Have you tried any other language as this presentation?
I'm sorry?
日本語でいいですか？全然喋る。日本語でいいですか？同じようなことを他の言語とかでやったことがありますか？
Do you have any experience with in other languages? Not Ruby, but the other languages. Do you have any experience?
Oh, yeah. I'm currently a mobile developer. And so a lot of my thoughts about this came from writing Java, unfortunately.
Have you tweaked the Java bytecode like this?
I have tried to, unsuccessfully.
Oh my god.
Yeah, I've been playing around with every compiler I can get my hands on, and this one was the most friendly.
Yeah, that's nice. Great.
ドットネットフレームワークとかについてどう思いますか？
Do you have any feeling about the .NET framework from Microsoft?
I don't have any experience with it.
Thank you.
Yep. All right, thank you all very much.